Good morning. My name is Matthias Fresacher, and today I'm going to tell you about the joint work I did with James East, Azeef Muhammed and Tim Stokes on finding categorical presentations for DRC semigroups. To begin with, I'm going to give you a quick overview of this talk, which is going to be a tale of two cities. On the one side, we have semigroups, and on the other side, we have categories, which we can think of as a collection of objects, a collection of morphisms that are maps between our objects, where every object has an identity morphism, and a composition operation of the morphism that is associative. On the semigroup side, our binary operation is defined for every possible pair. But on the category side, it's only defined for some pairs, specifically where the domain and the range need to match appropriately. So why do we care about categories? Well, because they need less information. So that then leads to the question, if I start off with a partial binary operation, can I recover the full binary operation? Spoilers, yes we can, according to the Ehresmann, and Buripard ESN theorem, but this was only true for inverse semigroups. Since then, there's been a large effort to try and generalize this to other groups of semigroups, other families rather of semigroups. And today I'm going to present to you the latest installment in this work for DRC semigroups. But this need for less information is somewhat misleading because sadly in this world, nothing is for free. The word category does a lot of heavy lifting on that previous slide because the category needs additional structure. And this is sort of where the missing information of the binary product is hidden. In general, the bigger our semigroup family, so if we say move from inverse to DRC semigroups, the more structure our category is going to require. So let's get into it. And we're going to be looking at DRC semigroups, and to give you some perspective, here are some common semigroup families that are contained within DRC, as well as some examples you might be familiar with. So obviously a DRC semigroup is a semigroup, and we have two unary operations D and R, which we call the domain and range. These satisfy some axioms. And to give you a bit of a sense of what they are, if we think of an inverse semigroup in the DRC sense, then our D and R maps are given as follows via the inverse. In terms of a history of this work, well, symmetry arises naturally in nature. This then led to the notion of an abstract group by Cayley in 1854. Similarly, symmetries arise in differential equations, and this led to the notion of the pseudogroup by Lee in the 1880s. Don't worry if you're not familiar with what a pseudogroup is. But there was no abstract structure for this pseudogroup. Two solutions were eventually found in the 1950s. The first using inverse semigroups by Wagner and independently Preston, and the second was using groupoids, and this was due to Ehresmann. And a groupoid is a category where every morphism has an inverse. Schein in 1965 then linked Wagner's and Ehresmann's work by providing a structure theorem for inverse semigroups where he makes use of groupoids. Then Buripard takes this one step further in 1979 by generalizing this inverse result to a regular semigroup. That then leads to the classical ESN theorem that we know today, as stated by Lawson in 1998. And this says if I take the category of inverse semigroups, in the category sense, that is isomorphic to the category of inductive groupoids, which I'm not going to define. Since then, there have been a number of generalizations, first by Lawson himself in 1991 to Ehresmann semigroups, and in the same paper to restriction semigroups. Before I can continue, we need to have a look at projection algebras. So let's take a semigroup S. Let's look at the set of idempotents, x equals x squared, and then sitting inside of that we have our set of projections. So where not only do we have an idempotent, our range and domain map are the identity map on that set of projections. There's an alternative equivalent definition, and this arises from the DRC axioms, where we can quite easily see that the image of the domain and range map is the same, and we can make use of that set to be our set of projections. This set of projections is not always going to be a subsemigroup, but it is a projection algebra where we have two unary operations, well in fact two families of unary operations, one for each element in our projections, and it's defined, well, for the feeders in terms of the R map and the delta in terms of the D map. Naturally, these need to satisfy some axioms. This is different to Peter Jones's original formulation of projection algebra, where he made use of two binary operations. but the two are equivalent via the use of these two identities. So then continuing on in the generalizations, we get to last year where East and Muhammed proved the result for the regular star semigroups. And also last year, D and Wang proves the result for DRC restriction semigroups. And I should note there are other generalizations by other authors in this area that don't quite neatly fit into this picture. A lot of work has been done in this space. So that brings me to the DRC ESN theorem. And this is the key result I want to talk about. So this is work from last year, and it was for the DRC semigroups. So it says if I take our category of DRC semigroups, that is going to be isomorphic to the chain projection categories. In terms of a proof of this result, well, first we need to find the right axiomatization of the category. For us, that is a biordered category. That is where the collection of morphisms has two partial orders on it, and those obviously satisfy some axioms. And we need the right structure on our objects, which for us is the projection algebras I just introduced to you. There are some applications of this work, particularly to being able to generate free projection-generated DRC semigroups, which we can just think of as a free semigroup, but obviously of a DRC variety. And also, we know that every projection algebra is the projection algebra for some DRC semigroup. This result was already known by Peter Jones in 2021, but he made use of different techniques. To conclude, the full details are available on our preprint. There are some very obvious future directions for this work to go in. And if I go back to the start where I said this was a tale of two cities, well, it really is just a tale of one city, thanks to category theory where semigroups and categories are very strongly linked.